So starting where we left off with problem 4, we are going to be transforming this equation into standard form. When it says using integers, that means you can only have negative or positive whole numbers. So as I mentioned earlier, we're going to have to do something with that fraction. But first we can go ahead and simplify a little bit. So we can start by using the distributive property. So I have y minus 2 equals negative 1/3 x, and then we have minus 2. So kind of getting rid of that there. Now the next thing I'm going to do is to bring that 2 over. So I'm just going to go ahead and add the 2 here. And we can see that those are going to cancel. So I'll be left with y equals negative 1/3 x. Now I want to get rid of the fraction. So that means I'm going to multiply by the reciprocal. So I'm going to multiply by negative 3/1 to both sides. And when you multiply by the reciprocal, that equals 1. And we generally don't write the 1, so we just have the x. And then over here, we end up with negative 3y. Now, there's still an issue because it needs to be, x and y need to be on the same side of the equation. So I'm going to move the negative x, or I should say subtract the x to move it over here with the y. So that would equal 0. And a lot of times they don't want you to leave the x as a negative, although I don't really care at this point, but some teachers care. So if we want to change that sign, that means we have to change all the signs. Basically, we have to multiply everything by negative 1. So I'm just going to change all of the signs and say, oh, well, if I multiply by negative 1, that would change all my signs. And that'd become a positive x. That'd become a positive 3y. And that would equal still 0. So some teachers care, but if you had your solution like this for me, I would be fine with that. But now it is in standard form using integers, which negative, positive, whole numbers. So it does require you to kind of think a little bit about your equations and how you solve equations, but we're just transforming it to get into standard form. Then we could easily find the x and y intercepts, and we could graph it if we wanted to, or go from there. So we're moving on to problem 5, using standard form as a model for an equation. So in this problem, a media download store sells songs for $1 each and movies for $15 each. You have $60 to spend. So write and graph an equation that describes the number of songs and movies you can purchase for $60. So kind of thinking about all those combinations. So I know I have $60 to spend, and I know I have either $1 for a movie, or I could do 15 for $1 for a song, or I could do 15 for a movie. So here is my equation. Notice it's in standard form, and I'm going to want to solve for my x-intercept and my y-intercept for this graph. So if I plug in 0 for y, I'm just going to be left with x is 60. And if I plug in 0 for x, I would just need to divide 60 by 15. So that would leave me with y is 4. So on the x-axis, I'm going to go over to 60. And on the y-axis, up to 4. So any combination then on that line would show that relationship, but here's the issue. Think about this problem. We talked about when problems are discrete or continuous. So obviously, not every point on the line here on the graph would work. I mean, you're not going to be able to buy half a song or half a movie. So that kind of presents an issue. So I think instead of connecting those, I would try to think, well, what combinations would make sense? So if I buy 5 songs, that's not going to let me also buy 3 movies, you know. So what about if I bought 15 songs, and that would allow me to buy also 3 movies? So that point would probably make sense. I'm just checking that real quick to make sure. Yeah, so that one works. We also could have a combination of 30 and 2. So that would work. And a combination of 40 and 1. So just kind of going along there. That seems kind of weird for me though. I'm sorry, it's 45 and 1. I was like, something's wrong here. So 45 and 1, yeah. So all of these points represent different combinations you could have, but I'm not going to connect them together because I know it represents a discrete relationship. So here's a summary kind of what we have talked about so far. And you're going to need to know all of these forms because they all have a purpose and they all have uses depending on the situation. So if we look here, we can describe any line using one or more of these forms of a linear equation. Any 2 equations for the same line are said to be equivalent. So here are forms. We have slope-intercept form, y equals mx plus b. So here's an example of that. We have point-slope form. So here's your formula, and this would be, again, an example. And then here we have the same line in standard form. Notice integers only. So being able to use those 3 forms, as I said, has their advantages. And this is kind of just a good summary of all the forms that we've done in this chapter up to this point. So each one refers to the same line, but they all kind of give us different information. One tells us the slope, one gives us another point that is on the line, one tells us the x-intercept and the y-intercept. So we get that information, different pieces of information from each form. Okay, so we're done with notes for today. So let me see in your packet here, wherever I put that. After section 5.5, there is another worksheet again, and it is again out of your book, but I have graphs for you and places to put your answers on. So you'll need your book, but you'll do it on this paper after the notes page, okay? So work on that, and we'll go through any questions you have when I see you again, okay? So talk to you later, guys.